Hello and welcome to online lecture number 15 for Chemistry 112 during the spring semester of 2020. In this lesson, we are still in chapter 17, and we're going to talk about several different topics, including the very important Nernst equation. As we saw in the previous chapter, delta G, the change in Gibbs free energy, is a very important property of a process because, among other things, it allows us to predict whether that process will be spontaneous or non-spontaneous. As we've already mentioned, for redox reactions, we also have cell potential, which also allows us to predict spontaneity. Specifically, if the cell potential is positive, it's going to be a spontaneous process. If it's negative, it's going to be a non-spontaneous process. So it should be no surprise then that E cell, standard cell potential, what we use to measure for redox reactions, is related to delta G, which is applicable for all types of reactions. Specifically, it says that delta G under standard conditions is equal to the negative of N times F times that standard cell potential, where N is a number of moles of electrons that are transferred in that balance equation. That's why we spent so much time on learning how to balance equations, because we need to know in a balance equation how many moles of electrons are being transferred. And then F is what's called the Faraday's constant. And it's a value we'll use not only in this context, but also a little bit later on, we'll talk about electrolysis. It's essentially, it's the total charge in 1 mole of electrons. So 96,485 coulombs per mole of electrons is our Faraday's constant we'll use for this equation and other equations. So in practice, we're going to calculate delta G under standard conditions for each of the following. So this is our reaction we looked at in the previous lesson. And those has a positive standard cell potential. So because it has a positive standard cell potential, we'd expect that delta G under standard conditions should be negative, because both properties tell the same story. They both say, they predict that this should be a spontaneous process. So we have our equation, delta G under standard conditions equals the negative of the number of moles of electrons times Faraday's constant times the standard cell potential. So the trickiest part about using this equation is determining what N is, how many moles of electrons have been transferred in this overall balance equation. And there's a couple different ways of doing this, and primarily it depends upon how you balance this equation, whether you use the half reaction method or you use the oxidation number change method. If you use the half reaction method, then one way you can determine N is by pulling out those half reactions, at least one of the half reactions. So we pull out the aluminum half reaction from the balance equation. It's already been balanced for us. This is what we'll have. Notice though that it is balanced by mass, but it's not balanced by charge. To balance it by charge, we have positive 6 total on the product side, 0 on the reactant side. In the half reaction method, I balance charges with electrons. And so to balance charge, I need to add electrons to the product side. Notice I had to add 6 electrons to the product side. Alternatively, if we use the oxidation number change method, we could look at the total oxidation number change for either what's being oxidized or what's being reduced. So for aluminum, for example, we have the reactant side, product side. Total, we have 0 on from aluminum. On the product side, though, we have 2 times positive 3 for a total oxidation number of positive 6 to give us a difference of positive 6, which is why we needed 6 electrons to balance out that charge. In other words, aluminum lost 6 electrons in this overall balance equation. So either way, we see that N, in this case, will be 6. So our calculation becomes delta G equals negative 6 moles of electrons times Faraday's constant, which is 96,485 coulombs per mole of electrons, times the standard cell potential. Standard cell potential is positive 1.21 volts. This is the number we calculated from the previous lesson. Recall, though, that a volt is a joule per coulomb. So to see that the units work out, we could also express this as positive 1.21 volts or joules per coulomb in SI units. So all the units will cancel except for joules. So our delta G, this process would be a negative -6 times 96,485 times positive 1.21 gives us a delta G of negative 700,481 joules, or more commonly, negative 700 kilojoules. So as expected, a positive standard cell potential will give us a negative Gibbs free energy under standard conditions. And notice that a relatively moderate standard cell potential, 1.21 volts, fairly easy to measure, is quite large negative delta G value, which indicates that this redox reaction we call a negative delta G value indicates that's how much maximally rather, the maximum amount of useful energy we can get out of this process. But at least theoretically, it's a fairly high number. And then one more example of converting from standard cell potentials to delta G. We have this example. We calculated earlier that previous lesson, this has a negative 2.91 volts, which means that as written, this is a non-spontaneous process. So a negative standard cell potential should indicate that the delta G under standard conditions should be positive. But in order to actually calculate what that number will be, let's apply this equation. And as we did before, the hardest part is determining what N is, how many moles of electrons have been transferred in this process. So if we use the half reaction method, this has already been balanced, both by mass and by charge. So if we pull out one of the half reactions, such as the magnesium being reduced, in order to complete the balancing of this half reaction, notice that we'd have to add electrons, and specifically, when we charge balance, we have to have 2 electrons. So the 2 electrons we had to add to the reactant side for the reduction half reaction would be the same 2 electrons we'd have to add to the product side for the oxidation half reaction. So in any case then, our number of moles of electrons is 2. So delta G under standard conditions equals negative 2 moles of electrons times Faraday's constant, 96,485 coulombs per mole of electrons, times the standard cell potential of negative 2.91 volts. So negative 2.91 volts, or joules per coulomb, gives us then a delta G value of negative times 2 times 96,485 times a negative 2.91 gives us a delta G value of 543 joules, or more commonly expressed as positive 562 kilojoules. So a relatively large negative standard cell potential has the same meaning as a very, very high positive delta G value. So remember that this positive delta G value indicates the minimum amount of energy we have to put into this non-spontaneous process to force it to occur. So in the previous slide, we looked at the relationship between standard cell potential and Gibbs free energy under standard conditions. There's also a relationship between the standard cell potential and the equilibrium constant K. That's this equation, which says that the standard cell potential is equal to RT divided by N times F times a natural log of the equilibrium constant. And so we can see there is these relationships between these 3 very important properties of describing a process: equilibrium constant, the delta G under standard conditions, and the standard cell potential. And if we know one, we can, with the right equations and constants and numbers, calculate the others. So notice that just qualitatively, that if K is greater than 1, it means at equilibrium you have more products than reactants. That means that the forward reaction is spontaneous, which would indicate then that this forward reaction would have a negative delta G under standard conditions and a positive standard cell potential. The reverse would be true if K is less than 1. And if you're already at equilibrium under standard conditions, then K is equal to 1. If you're at equilibrium, delta G under standard conditions is equal to 0. And then if you're at equilibrium, standard cell potential is also equal to 0. In the previous lesson, we were interested in calculating standard cell potentials. In other words, cell potentials where everything's in its standard state. And to do that, we'd use this equation, which allows us to calculate the standard cell potential from the standard reduction potential of the cathode minus the standard reduction potential at the anode. These potentials, these numbers that we get from a table in a textbook or another resource are also referred to as electrode potentials. In any case, this number we can calculate from these numbers, but this number is only applicable when all the reactants and all the products are in their standard states. But in reality, when we're actually doing experiments, it's very rare that we actually would run an experiment where everything was in its standard state. Normally, things are done under non-standard conditions. So, like we saw with delta G in the previous chapter, you can relate delta G under non-standard conditions to delta G under standard conditions. Likewise, we can relate E, cell potential under non-standard conditions, to E with a degree sign, the cell potential under standard conditions. And that's what's using what's called the Nernst equation, which says that the cell potential under non-standard conditions is equal to the cell potential under standard conditions, so a number we can calculate using this equation, minus 0.0592 volts divided by N times the log of Q. And strictly speaking, this somewhat simplified equation is only applicable when we're at a temperature of 25 degrees Celsius. That's where this number comes from. So in any case, this N is the number of moles of electrons transferred in the balance equation. It's the same value of N that we used in the previous slide to calculate delta G under standard conditions from the standard cell potentials. And Q is your reaction quotient. That ratio of the concentration of the products raised their coefficients divided by the concentration of the reactants raised their coefficients. So a couple examples of applying the Nernst equation. We have this example we looked at very early on, and we want to calculate the cell potential under non-standard conditions. Specifically, when the concentration of copper 2+ ions is 0.025 molar, the concentration of zinc 2+ ion is 1.10 molar. We know from the previous lesson that we've already calculated that using these values, we can calculate the standard cell potential as 1.10 volts. And then we want to use this equation, Nernst equation, to calculate the cell potential rather under non-standard conditions. So when we plug in our numbers, so we have our Nernst equation. So we can plug in our numbers. We have the standard cell potential, which we already calculated as positive 1.10 volts, minus room temperature, 0.0592 volts, divided by N. N is the number of moles of electrons transferred. So as we did before, we can figure that out from the given balance equation. So if we break apart the reduction half reaction, pull that out, go from copper 2+ to copper element to copper, there has to be an addition of 2 electrons in order to be balanced by charge. So 2 is how many moles of electrons are involved, times the log of Q, where Q is the concentration of the product divided by the concentration of the reactant. And elemental zinc and elemental copper are solids, so they're excluded from our Q expression. So we have E is equal to positive 1.10 volts minus, this simplifies slightly to 0.0592 divided by 2, 0.0296 volts times the log of concentration of zinc, 1.1, divided by the concentration of copper, which is 0.25. So the E is equal to positive 1.10 volts minus 0.0296 volts times the log of this ratio, 1.1 divided by 0.025 is 44. So then E is equal to positive 1.1 volts minus 0.0296 volts times the log of 44, which is positive 1.643. So finally, we get there, E is equal to positive 1.1 volts, the cell potential under standard conditions, minus this product, times 0.0296, minus 0.0486 volts. So 1.1 minus that number gives us a cell potential under these non-standard conditions of positive 1.05 volts. So it's still a spontaneous process under these non-standard conditions, but it's the standard cell potential. The cell potential itself is not as positive under these conditions as compared to these standard conditions. So one conclusion we could draw from that is that at least under these non-standard conditions, yes, it's spontaneous, but at least theoretically, we can't get as much useful work, maximally useful work, out of this process under these conditions as compared to these standard conditions. In another very similar example, reaction between aluminum and Fe2+ under these non-standard conditions, and we have to calculate the cell potential under these non-standard conditions. So we use our Nernst equation. For the Nernst equation, we need the cell potential under standard conditions, which we previously calculated as 1.21 volts. We plug in what we know into the Nernst equation. The cell potential under non-standard conditions is equal to the cell potential under standard conditions. We plug in what we know. The standard. We plug in what we know. The cell potential under non-standard conditions is equal to the We plug in what we know. The cell potential under We plug in what we know. The cell potential under non-standard conditions is equal to the cell potential under standard conditions, 1.21 volts, minus 0.0592 divided by N, where N is the number of moles of electrons transferred in this process. So we can see from the balance equation, or as we saw before, we can pull out the half reactions if we need to, or look at change in oxidation numbers. In any case, we see that each aluminum atom goes from oxidation number of 0 to positive 3, a difference of 3. So each aluminum atom loses 3 electrons. There are a total of 2 aluminum atoms in this balance equation. So in total, we have 6 electrons being transferred. So 6 would be our value of N times log of Q, where Q is our reaction quotient. It's equal to concentration of aluminum on the product side squared divided by concentration of iron on the reactant side, and that number has to be cubed. We plug in our numbers. E is equal to positive 1.21 volts minus 0.0592 volts divided by 6 times the log of concentration of aluminum, which is 0.01. And that has to be squared, according to our Q expression, divided by the concentration of iron, which is 1.0, and that number is going to be cubed. So that's our Q expression, just numbers we can plug in. And so E is equal to positive 1.21 volts minus 0.0592 over 6 times the log of this ratio. So we have 0.01 squared divided by 1 cubed is equal to 1.0 times 10 to the minus 4. And then further simplifying everything, positive 1.21 volts minus 0.0592 divided by 6 is equal to 0.009867 times a log of 1 times 10 minus 4, negative 4. This would be volts. So finally we have E is equal to positive 1.21 volts minus this product, so negative 4 times 0.009867 gives us a negative 0.03947 volts. So our cell potential under these non-standard conditions is 1.21 volts minus this value, or 1.21 volts minus that number, gives us a still positive 1.25 volts. So this process is still spontaneous. And in fact, it's actually more positive under these non-standard conditions as it is under the standard conditions. So at least theoretically, under these non-standard conditions, we should be able to get maximally more useful work out of this process under these conditions as compared to the standard conditions. An interesting application of the Nernst equation is it allows us to calculate and predict the cell potential for what's called concentration cells, where it's a galvanic cell where both electrodes have exactly the same identity. So for example, in this case, we have both zinc as the electrode on the anode side, as well as zinc as the electrode on the cathode side. And we can calculate under these conditions what the cell potential should be. And we can do so using our Nernst equation. So we have our shorthand notation. So we first need to interpret the shorthand notation to determine what is being oxidized, what's being reduced. In other words, what's occurring at the anode, what's occurring at the cathode. So recall that in the shorthand notation, the convention is always describe the anode first, followed by the cathode. So at the anode is where oxidation occurs. So the oxidation process would be zinc being oxidized to zinc 2+, losing 2 electrons. And the cathode is where reduction takes place. So that would be zinc 2+ on the cathode side, accepting those 2 electrons to become reduced to elemental zinc. So then the electrode potentials for both the anode and the cathode are identical to one another because we always define the electrode potentials as the standard reduction potentials as reduction potentials. And this value is negative 0.76 volts for both these processes. Remember, this is defined as a reduction potential, even though, as we know, oxidation is actually what occurs at the cathode. So to calculate the cell potential in these non-standard conditions, 0.1 molar for the anode zinc concentration ion and 1 molar for the zinc 2+ ion concentration at the cathode. We have to first calculate the standard cell potential. That's equal to, of course, the electrode potential of the cathode minus the electrode potential at the anode. But because both the cathode and the anode are the same material, they're both zinc, they both have the same electrode potential. So as a result then, standard cell potential is always going to be, for these concentration cells, always going to be negative 0.76 volts minus a negative 0.76 volts. As a result, because of the same 2 numbers, this difference, of course, is always 0.0 volts. So under standard conditions, having the same 2 electrodes, there's no driving force to push electrons away from the anode and toward the cathode. That's under standard conditions. We don't have standard conditions here, so we want to calculate what the cell potential should be under these non-standard conditions. So for that, we use our Nernst equation. So E is equal to E naught minus 0.0592 volts divided by N, number of electrons transferred, times the log of Q. Plug in our numbers, we have E is equal to the standard cell potential, which is 0.00 volts, minus 0.0592 divided by N, number of electrons transferred. Notice that both for the oxidation as well as reduction, in the balanced half reactions, we have 2 electrons. That's what N is equal to, times the log of Q. And the log of Q is going to be equal to the concentration of zinc 2+ as a product. So that's in the anode side, that's a 0.1 molar to the first power, divided by the concentration of zinc 2+ on the cathode side, which is 1.0 molar. So then we get a value, slow simplification, 0.0592 divided by 2, log of 0.1, which is -1. So then we get E is equal to 0.00 volts, 0.00 volts, minus 0.0296 times a -1 to give us a positive 0.0296. So 0 plus 0.0296 volts gives us then a cell potential, predicted cell potential of positive 0.0296 volts. So the process is spontaneous, but it has a very, very low overall cell potential. Cell potential that's a little bit less than 30 millivolts. But the process does occur, but because the cell potential is fairly low positive, we wouldn't expect even maximally very much useful work out of this concentration cell. So if we had this galvanic cell, copper 2 plus zinc produces copper and zinc 2 plus, and we could certainly calculate the cell potential under any condition using the Nernst equation, specifically 1.1 volts minus 0.0592 divided by 2, because 2 electrons are transferred, times the log of Q, which is just the current concentration of zinc 2 plus ions on the product side and the concentration of copper 2 plus ions. As this reaction proceeds, though, as copper 2 plus is reduced to elemental copper, and as consequently zinc is oxidized to zinc 2 plus, what's going to happen is that eventually, as time goes on, the zinc 2 plus concentration is going to increase. The copper 2 plus ion concentration is going to decrease. As time goes on, reactants are consumed, products are produced. As a result, this ratio gets larger in time. So therefore, what we're subtracting off of the standard cell potential, this part of the Nernst equation, it also gets larger. Very slowly, but it does get larger until eventually what's subtracted from 1.1 volts equals 1.1 volts until the cell potential equals 0 volts. At that point, you're at equilibrium, and therefore there's no more long driving force to push electrons away from the anode towards the cathode. So under those conditions, then, our Nernst equation simplifies a little bit. So when we're at equilibrium, in other words, E is equal to 0. Also, equilibrium Q becomes K. And then a little bit of rearrangement, we get this equation, which relates the standard cell potential to our equilibrium constant. We can use this equation to calculate K if we know the standard cell potential, or if we know K, we can calculate the standard cell potential. So to give you an idea, we won't go through the actual example, but to kind of give you an idea as the magnitude of these values, a standard cell potential of 1.1 volts, plug in the respective numbers to solve for K, we get a K value of 1.5 times 10 to the 37. So an equilibrium constant we probably couldn't measure directly because it's such a very large number. That means at equilibrium, we have very, 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 very low concentrations of reactants, probably too low to actually directly measure. But if it's a redox reaction, and if we can measure the standard cell potential, then from the standard cell potential, we can then calculate what K is. This is especially useful when K is either very, very large, as in this case, or when K is very, very, very small. This reaction we saw was non-spontaneous, has a standard cell potential of negative 2.91 volts. And so we saw for positive standard cell potentials, we get a very large value of K. What happens when we start off with a negative standard cell potential? So we can plug in our values and calculate K using the information we know. So because we're asked to solve for K, one place to start would be do the algebra to rearrange this equation to solve for K. So to do that, I can first divide both sides by this ratio. So when I do so, I get N times the standard cell potential divided by 0.0592 volts is equal to log of K. And then to directly solve for K, I take the anti-base 10 log. So in other words, raise both sides to 10. So we have K is equal to 10 to the N times E divided by 0.0592 volts. So that's our equation that allows us to directly calculate K if we know what E is. So to plug in the value of the standard cell potential E, negative 2.91, is equal to 10 to the number of moles of electrons. We saw before that's 2, times the negative 2.91 volts divided by the 0.0592 volts. So our exponent simplifies to 2 times negative 2.91 divided by 0.0592, negative 98.31. And you take 10 to that number, we get almost an impossibly small number. And some of your calculators may not even be able to simplify it as 4.89 times 10 to negative 99. So with a negative standard cell potential, a negative almost 3 volts, we get an almost impossibly small value of K. So certainly in this case, if we try to measure K directly by determining the concentrations of the products and reactants at equilibrium, we probably won't be able to do so because this number indicates that at equilibrium, we have such a small, almost minuscule concentration of the products that we want to be able to actually directly measure it, at least reliably measure it. So we've seen in this lesson how to calculate the cell potential under non-standard conditions using the Nernst equation. And just as importantly, we've also seen how we can relate the standard cell potential to the Gibbs free energy under standard conditions and or the equilibrium constant. And of course, these are also related to one another by equations that we talked about in the previous chapter. So the next lesson, then we'll get into some applications of these redox reactions.